40 out of 40. You might have seen some people got full marks, 40 out of 40. So how many got 40 out of 40? Out of the 84. And how many got 39 out of 40? 38.5. So there is no 39.5 because we just made it into 40. 38, 37, 36 also, let's say. 35. So out of 84, somebody wants to guess? What? 13 to 15 total, how many? 40 out of 40. There were 15 this one. Okay, so this is actually 11, this is 9, this is 4, this is 2, this is 5, this is 7, and this is also 5. Okay, so count how many. So 20, 24, 26, 31, 38, and then 38 plus 5 is 43. So this is like 43. So out of 84, so half of 84 is 42. So more than like it has half of the class is in this range, 35 to 40. So what does that indicate? The paper was very easy, so that is indicate. So but then it is confirmed that at least you can write the easy paper. So we'll see how it goes. So this is first thing I want to say. Other is that we have lost some classes actually. Slowly they were not managing. So next holiday we are getting is Ugadi, 31st March. And then I also came to know that 14th April will also, it's not announced, but I think due to some Ambedkar Jayanti also, that day also will be not working. So 3 classes we are going to miss. So at least 2 classes I want to take extra apart from the regular thing. I think from now we have about 6 lectures, but I need maybe 2 more or so something like that. So what do you think is the best time for doing that lectures? Except Saturday, Sunday. What? Wednesday, what time? 2:30 to 4. You just confirm that. So one option is that Wednesday 2:30 to 4. Which Wednesday? Next week onwards or? Yeah, next week onwards. So there will be one on Monday, Wednesday and Thursday. Mondays anyway. Holidays. So maybe 2 Wednesdays I think maybe next one or the other next one. I think anyway the marks are both, so you can afford to take more classes and cover more subjects. There is another option, okay? Friday 2:30. Just I take two weeks like this, so not on both times, but so which one do you prefer? Wednesday or Friday? Option 1. Anyone? So yeah, so maybe I'll send a mail. So but at least yeah, I get to do this. So with that, let me come to this. So actually, after considering this, maybe next class I will give you some kind of schedule again, like which day, which topic I want to cover. So we have usually 2. So one is the oh, volume is quite high, so I'll just speak slowly. So one is the load flow and the optimal power flow, that is OPF or that kind of topic, and the other is I think this fault calculation that we are doing now. So anyway, let's go ahead with today's thing. So I'll call this lecture 15, and this is about symmetrical faults. So we'll just see what is that topic, but I wanted to refer to one of the questions that we gave in the midterm exam. So we will use that for our calculations today. So the question was something like this. I'll just draw the diagram. You've already seen this in the exam, so it's nothing new. So I'll just put it like this. So this is J0.5, J0.1, J0.2, 25, 1 to 5. So this is 1, 2, 3, 4, 5 and 6. So this is a 6-bus system that you have, and we were trying to analyze this 6-bus system in the midterm exam. So you already attended this question and most of you got it correct. So we'll use this as the example problem today. So the question that we are now asking is, what happens in the case of a 3-phase balance fault occurring on different places on this network? Okay, so because the problem was only about defining what is the Y bus or what is the Z bus, we are not given any information about where is the generators, where are the loads and so on in the system. So assume that there might be a generator here, there might be another generator here, and then the power is flowing like this, and then there may be load at 5, 4, 6 and different loads are there. So some kind of power flows are going on. So that's what we call as base case. So base case is a situation where you have generators and loads and network, and then the base case some powers are flowing. Over and above that base case, if there is a fault, what happens? So first of all, what is a fault? A fault is that whenever there is this high voltage bus bars are there, or high voltage equipment, high voltage device is there, that is suddenly short circuited to the ground or to each other, and then unintentionally some high current will flow. Because of that high current, we call it as a short circuit or fault. And what is the remedy for that fault? We have to kind of disconnect the particular device or equipment which is undergoing the fault. So, so what I want to do now is, we had this load flow studies. So for that, Y bus was very useful. So load flow, all these load flow equations, everything, we are using Y bus. But if you want to do fault calculations, if you want to study faults, Z bus is very useful. Okay, so Z bus is quite useful for doing the fault calculation. We will see that. But to begin with, I'll say without Z bus, how we will address this problem. Okay, so for that I want to add some more information to this network. So let's assume some generators and things like that. Okay, so if you notice, because the problem was kind of simplified problem that I gave in the exam, only one connection is there with the ground. So what you can imagine is that at this bus number 1 there is a generator. Okay, so I'll write it like this. This is bus number 1, and then there is some impedance and then some generator. So this is generating the power, and then this is let's say the same value, J0.5. So this is the impedance. Okay,
So now how this generator became short circuited here. So what we are trying to do is I can replace this voltage source in series. This is a voltage source. So this voltage source in series with a impedance, you can replace it with a equivalent current source. It's called Norton's equivalent. So this will become something like this. So this is a current source, and then this is a J0.5. Okay, like this I can replace this. And then since our problem in the question was only about calculating Y bus, calculating Z bus, I am not interested in this how much current is coming here. So I wanted to include this within the problem on the calculation of Y bus. Therefore, this branch was neglected. Then it became like this, J5 and J0.5, and then this one came in the question like this. Okay. So okay. So very sensitive. So this was the problem. So now what I want to do is I want to add back that machine. Okay. So assume that at bus 1 there is a generator, at bus 3 there is a generator. Okay, so this is our assumption. And then at bus 5, 4 and 6 there are loads. Okay. Now the loads, you can consider that loads are, because we are doing fault calculation, the load current and the fault current will be usually like 3 times or 4 times or 5 times that of load current. Okay. So one convenient assumption that people make is that the base case currents are 0. So there are no loads and all these things, so that it is easy to do your calculation. But then if you want to do the actual calculation, you need to also consider the this one load current also. Okay. So the problem, I'll start with the problem directly. So when I write like this, there is a generator at bus 1 and then there is a generator at bus 3. So what is this J5 indicate? This J5 indicates the reactance of the generator. Okay. So what kind of reactance? So there are 3 types of reactances. Generator reactance. So first of all, generator impedance, that means the resistance and reactance, but you assume that resistance is 0, so there is only reactance, and that reactance also, there are 3 types. What is known as subtransient reactance. So this is usually indicated with X, D, double dash. Okay, so this is normal notation, subtransient reactance. I'll explain what it is. Then there is a transient reactance. So that is XD, single dash. Okay, and then there is a reactance. So that is denoted as XD. Okay, so why these 3 different types of reactances are there? That is has something to do with the construction and the design of the machine itself. The synchronous machine, so a generation means it's a synchronous machine, is designed in such a way that it will exhibit 3 different values of reactance. Okay. Now usually or actually it is, the design is something like this. So the value of XD double dash is greater than the value of XD dash greater than the XD. And how to determine which one to use? Okay, so the general thing is, this is like up to 2 cycles. This is maybe 2 to 5 cycles, and then this is more than 5 cycles. So when I say cycle, what does that mean? It is a time period of your AC waveform. Okay. So if you have a waveform of 50 hertz, the time period will be how much? 1 by 50, that is 20 milliseconds. So in 2 cycles means 20 plus 20, 40 milliseconds. For the initial 40 milliseconds, the behavior of the synchronous machine, it will exhibit XD double dash as the reactance. Afterwards, between 2 to 5 cycles, this is all approximate numbers, between 2 to 5 cycles, its reactance will slightly reduce. And then later on, this is what we normally use for our regular calculations. So, because fault is a sudden thing, whenever there is a fault, it's like a sudden occurrence. So, immediately after the fault, you have to use these values, and then later on, after a few cycles, you have to use the other values. Okay, I think at this time we can also discuss what happens actually. So, this is a, let's say this is my time axis. Okay, so consider some part of the network. Let's say this is a network, and then there is a circuit breaker here, and then there is a generator here. This generator is generating power, and then there is a circuit breaker. So if there is a fault at 2 or there is a fault at 3, a large current will flow from this generator, and this circuit breaker will detect that, and then it will disconnect the generator. So what happens? So first is, so let's say at this point, fault has occurred. So once the fault is occurred, after some time, there will be a trip coil energized. So what there is a measuring device here which measures how much current is flowing, and then there is a relay. That relay will take the decision that okay, the current is normal or the current is abnormal, very high. Depending on the relay decision, there will be a signal called trip signal. So the trip signal will go to the circuit breaker, and whenever the circuit breaker receives the trip signal, it will open the network, it will open the connection. Okay. So this mechanism, detecting of the current and then taking the decision and then sending the trip signal, so that is this one. So some time goes there itself, okay, few milliseconds. So after the trip coil is energized, so if you look at the circuit breaker, it will be something like this. This is the line, and then there will be a mechanical contacts like this. So and then this whole thing will be inside one enclosure. Okay, and these two, it can be moved. So normally they are in contact like this, and in between there is oil or there is some SF6 gas or something like that. So when the trip signal is received, it will separate the contacts. Whenever you any electrical connection, when you disconnect, first you will get some spark or arc. Okay, so there will be an arc. So this is an arc. Okay, after some time the arc will be extinguished because of the gas that is present or oil that is present and so on. Okay. So this arc is always there. So even this switch that you use in your house, so when you switch on the light or fan, that arc is always there. It will be there for very few milliseconds or something like that. So once the trip coil is energized, contact separated. Okay, so contacts are separated, and then arc will start, and then after some time arc is extinguished, or arc is extinguished. So I think the time between these two is the operation time of circuit breaker. Okay. Now the operation time of circuit breaker is somewhere maybe between this 2 to 5 cycles. Okay. So this XD double dash is already present when the circuit breaker is still working, closed. by the time the circuit, sometimes even circuit breaker operates after this also. Okay. So if I want to do fault calculation, I should use this value. And if I want to do the regular load flow calculation, I should use this value, xt. So all this history is only for that small point, that whenever you are doing the fault calculation, you have to use this one. So the manufacturer of the machine will specify these three values separately. Okay. What? Okay, I think now the sound is a little less. Let's go ahead now. So the conclusion of all this discussion is that this XD double dash should be used, which is anyway specified by the manufacturer of the machine. Okay. So now we'll come to the actual problem that I wanted to work today. So the assumption is like this. Before fault, all currents are 0. So this is only a simplifying assumption that before any fault is there, the base case, the currents are 0 for this circuit. Okay. And then also all currents are 0, all voltages are 1.00 degrees. Okay. So all bus voltages, voltage at bus 1, bus 2, bus 3, bus 4, bus 5, bus 6, all the voltages are 1 angle 0. So normally what is the procedure? This is not the procedure. What you will do is you will solve the load flow problem. The results of the load flow problem is you will know what are the unknown states. You will know all the voltage, actual voltages of all these buses. But we don't want to do that. So it's a simplifying assumption that all the voltages are 1 angle 0. So it's a simplifying assumption. And all the currents are also 0. So in fact these two are obvious, because suppose if the voltage here is 1 angle 0, the voltage here is also 1 angle 0. Angles are same. There is no angle difference, so there won't be any current, and all the currents are also 0. So it's just a simplifying assumption. Under this situation, let's choose where do you want to get the fault? 4. Okay, so fault at bus 4. Okay. So fault at bus 4. Now usually the fault is represented like this, so some kind of arrow. Now the fault will have some fault impedance also, but right now we are assuming that the fault impedance is 0. That means what? The impedance between this point and the ground, there will be some impedance that we are assuming 0. Okay. So the question is, find how much current in the fault. So how much current is flowing in that fault if there is a fault? And the use for that is that if I want to put a circuit breaker there, I should know how much current it has to withstand to break it. So for the designing of the circuit breaker. So without using JetBus, if I give you this problem, how will you solve? Actually, you can right away go ahead and solve it also. How will you solve this problem? So the problem is like this. So the voltage here is 1 angle 0 degrees, 1 angle 0 degrees. So 1 angle 0 degrees. All these voltages are there. Okay, suddenly there is a fault here. Okay, so how much is the fault current? So that is the question. How much is the fault current? So how will you solve this? So just think about it. So think about your regular circuit calculation. So what will you do? The hint that I want to give you is think about Thevenin's theorem or Thevenin's network theorem and all. So what is a Thevenin's network theorem? You can replace the entire circuit with one value of voltage. So let's say VTH and one value of impedance ZTH, and then this will be your bus 4. Okay, and then this is our fault. Okay, so I want to replace this entire network with just this one, and then I can calculate the how much is the fault current. So how much is the fault current here? This divided by this, because there is no impedance in the fault. Okay. So what is VTH? VTH is the open circuit voltage. So suppose if I put a voltmeter at bus 4 and measure the voltage, how much voltage I will get? That itself is VTH. Okay, which we already know, that is 1 angle 0 before the fault. Okay, so VTH is 10 degrees. Now I want to calculate what is the Thevenin's impedance. Okay, so how you want to do that? So all voltage sources will be short circuited and all current sources will be open circuited, and then you will take the circuit and then you will draw this thing and then do that. So for this circuit, the way we formulated the problem, we are not including any machine at 3, at 6 and at 5. We are including only one machine at bus 1 as per your midterm question. Okay, because I wanted to match to that. So I just said there is a machine at 3, but for the time, just to match to your paper, I am just removing that. So assume that there is only one generator for the entire system. Okay, bus 1 there is a generator. At bus 3 there is nothing. At bus 6 and 5 also there is nothing, because I said that currents are all 0. Okay, so just so that it is easy for you to solve it. Now if I draw the circuit will be like this. So there is a voltage source here that is short circuited. So this voltage source is short circuited. So I have ground, and then this is J 0.5. Then this is bus 1. Then there is J 0.1. Then this branch which is going from 2 to 3, this is open. So it's just open circuited, whatever is the value. Then there is this J 0.25. Okay, here bus 4 is there. This bus 4 there is a short circuit, and then there is another branch going to bus 5, another branch going to bus 6. But since these two are anyway open circuited, I am not interested in that. So Thevenin's impedance, that means if I measure the impedance between these 2 points, I have only this path. Okay, so from here it is like this. So what is the Thevenin's impedance? 0.25, series 0.1 and series 0.5. So addition of these 3. So that will be your ZTH. How much is that? 0.25 plus 1, 3.5, 0.85. So this is your Thevenin's impedance as per the circuit given. Okay. Now what if I consider a machine here, there is a generator here, okay, already some impedance has to be given, but that impedance, if it is given, then you can consider here there is a machine and then it's a impedance and then short circuited. Then how will you solve it? Let's say this impedance XD double dash is 0.3, okay, then how will you solve it? So the circuit will be like this, J 0.5, this is grounded, then J 0.1, okay, then this between 2 to 3, how much is that? 0.2, then there is bus 3, here there is J 0.3 and then this is also grounded, and here there is J 0.25 and this is bus 4, and then this is there is a fault here. This can be neglected, this can be neglected because they are open. So now what is the impedance from here to the ground? So this branch and this branch are parallel. So this is 0.6 and this is 0.5. Okay. So equivalent will be like this. Let's say this is the ground. 0.6 J, 0.5 J, then 0.25. Then this is my bus 4 and this is again ground. So I want this impedance between these two. Okay. So these two are parallel. So how will you calculate? 6 into 5 divided by 11. 0.03 by 0.11. How much is this? So let's some number you will get. How much is that? No, this is 0.3. 0.3 by 0.11. So 8. So 0.27. Okay. So this 0.27 in series with 0.25. How much is that? 0.52. So my Z Thevenin is 0.52. Okay, so like this you will calculate the Thevenin's impedance. Okay. But just to match with our earlier solution, I am not considering this machine. There is only one machine for the entire system. So this you can, for the timing you can not worry about. So for all practical purposes, our ZTH is 0.85. So you notice that the Thevenin's impedance is reducing. Okay. So why the impedance is reducing? Because I am adding another parallel path. Okay. So now comes the final question. This one. Find how much is the current. Okay. How much is the fault current? So let me take this out. So how much is the fault current? So I fault. So I am just using this notation. I fault during the subtransient period, initial first 2 cycles. So that will be VTH divided by ZTH. So 1 angle 0 degrees divided by 0.85. Okay, 0.85 angle 90 degrees because this is J. Okay, so 1 by 0.85. How much is that? Can someone quickly calculate? One by 0.85. How much? 1.15 per unit. Okay. So just assume it's 1.15. So this is the general calculation without using Z-bus, just based on your this one. So now you can imagine if there are a lot of lines, if there's a line here, if there's a line here, and there are a lot of lines, all the time your time is wasted in doing this network calculations to find out the Thevenin's impedance. Okay. Now I can extend the question. I can say voltages at 1, 2 and up to bus 6. All the bus voltages after fault. Okay. After the fault is over, what are the bus voltages? Like during the fault. Okay. So how will you calculate that? How will you calculate that? So just look at this current. Okay. So that 1.15, current is flowing from 2 to 4. Okay. Current from 4 to 5 is 0. Current from 4 to 6 is also 0. So therefore, voltage at 5, voltage at 4, voltage at 6 are all equal. Okay. So V5 equal to V4 equal to V6 equal to, after the fault it is 0. Okay. Once the fault is there, it is 0. Because this is directly short circuited. And the fault impedance is also 0. Now this 1.15 is flowing in J0.25. So how much is the voltage drop? So 0.25 into 1.15. So can you quickly do that? How much is that? 1.15 into 0.25. Point? How much? Point? 0.9? 0.29. Okay, let's assume it is 0.29. So I think J will be, yeah, J will be multiplying, right? Oh, two J's are there. There's a J here and there's another J here. So it will be like that. So 0.29 per unit. Okay. So what you notice here is, if the 1 per unit, 100% voltage, let's say it is 11 kV. So you are only getting 29% voltage. So severe voltage dip. So when there is a fault in the network, the neighboring buses will experience a severe voltage drop. Okay, now 100% voltage become only 29% voltage, 0.29 per unit. So what is voltage at 3? V3. So voltage at bus 3. Because I am not considering any generator here for our problem. So there is no current between these two. Therefore the voltage of 2 and 3 are equal. So voltage at 3 is also 0.29. So what is voltage at bus 1? Voltage at bus 1. So the current here is 1.15 per unit. So that current is also, the same current is flowing like this. So that current multiplied by 0.1. That much voltage drop, you add it to this, you will get the voltage at 1. So 0.1, that is 0.115. 0.115 will add it to 0.29. So 115,504. So 405 per unit. So like this I can get the voltages at different buses at that fault. Okay. So I can now repeat the problem and then say, instead of bus 4, what if the fault is at bus 6? So how will you do again? You have to repeat the entire procedure. If the fault is at bus 6, again Thevenin's voltage is 1 angle 0. What is the Thevenin's impedance? So you measure from here this plus this plus this plus this, because there are no other parallel paths. So if there is a generator here, again you have to keep doing all that network calculation. So I think you are getting the idea. So any place the fault is given, then you have to find the Thevenin's impedance and then you have to do like that. Okay. So this is about the method without using Z-bus. And if some impedance is given, then you can consider that in your this circuit and then find this one and all. So usually this is actually 1.15 is quite less. Usually it will be more also. This is like 15% more than the full rating current, but usually this will be even more because our problem is little artificial. Okay, so remember the answers. Let me write down the answers here. 1.15, this is my fault current, and then the voltages are 0.405, 0.29, 0.29, and then 0, 0, 0. So this is my V. Okay, so let me just now do the same problem in a much simpler method. But for that we require the Z bus. Okay, let me write the Z bus here. So you already solved this problem in the exam. So what is the Z bus for this circuit? So first step 0 to bus 1. Okay, J.5. So I'll write J.5. Okay, second step adding bus 2 to bus 1. So J.1 is added. So what will you do? You copy the row. So J.2, J.5, J.5, and then you take this point Z11 plus Z2. So this will be 0.6. Okay. So this is 1 and 2. Then bus 3 is added, J.2. So copy the second, because it is a new bus connecting to old bus 2, copy the second row. So J0.5 copied, J.6 copied, J0.5 copied, J.6 copied. Now here this Z22 plus the new impedance, which is also 0.2. So 0.6 plus 0.2, 0.8. Okay. So this is the third bus is added. And then add the fourth bus, second bus. Because most of the people made a mistake here. They copied the third row into all that. But fourth is connected to second. So 0.25 is connected to the second. So what you do is you copy the second column to the fourth column. So second column copy to fourth column, J.5, J.6, J.6, J.5, J.6, J.6, and then here you take the Z22, which is 0.6, to that you add the new impedance 0.25. So it will become 0.85. Okay. So this Z22 plus 0.25. This is fourth. Okay. Now what is the next step? For 4 I am adding 5, or I can add 6 also, but then because I am following the same numbering, so 4 I am adding 5. So what happens? Copy the fourth row to fifth. So just I am copying same. Just copy the same. 0.6, 0.6 and 0.5. Now here I'll take the Z44 and add the new impedance. How much is that? 125. So 0.85, 0.125. So 579. So here it will be 0.975. So this is my fifth row. Okay. Again I want to add the sixth row to fourth row. So what I have to do? Copy the fourth row again. So this is 6. So copy 4 to 6 because we are connecting a new bus to bus 4. So 4 to 6 it will be J.5, J.6, J.6, J.85 and then J.85. Again copy 1, 2, 3, 4th, this one. So 0.5, 0.6, 0.6, 0.85, again 0.85. Okay. So here what I have to do? Here you take the 4, 4, that is this one. Z44 plus new impedance, which is this one. Okay. So this will be how much? 0.85 plus 0.1111. So 1169. So 0.9611. So this is, so that way I just reviewed your midterm question also. So we have the Z bus now. Okay. Now looking at this Z bus, I want to solve this problem. Okay. Fault at bus 4, find out the fault current. Okay. Now automatically the Thevenin's impedance is calculated. Okay. What is the Thevenin's impedance for bus 4? So this one. So in fact the Z bus itself is already containing the Thevenin's impedance of all buses. Okay. So what is the Thevenin's impedance for bus 6? This one. Okay, so if you look at this circuit, if I ask you what is the Thevenin's impedance here, so there is only one ground here. So this in series with this, in series with this, in series with this. So which one is getting added? This one, this one, this one, and this one. So the same things were getting added here also. Okay. So that way we can easily, quickly get the Thevenin's impedance of the buses. Okay. So now if I want to calculate fault current at bus 4, so IF4 double dash is equal to 1.00 degrees divided by J 0.85, that will be 1.15 per unit. Okay, so this was my calculation. I think some J should be there, but we are just worried about the magnitude now. So this is my fault current, I can directly calculate. So fault current at bus 6 will be 1.0 divided by 0.9611. So that some number will come. So if you calculate your Z bus once, then fault calculations become faster. But what about the voltages? Okay, how much is the voltage? Okay, so I'll give you a simple formula. The formula is like this. Let me just write it down. We'll derive it also. So Vj is equal to Vf minus okay. So we'll work on this formula. We'll derive this formula. So let me give you the notations first. I'll just put K for. So the notations is like this. K is the bus where there is a fault. So K is equal to 4. So this one can be 1, 2, 3, 4, anything. Okay. So what is V1? V1 equal to V4 minus this one, Z14 into I4 fault. Okay. So what was our fault current? Fault current is, so let me write it here. V4 is 1 angle 0. This is before fault. Okay, I'll just put 1 minus before fault. And what is Z14? First row, fourth column. That is J.5. Okay. Multiplied by what is I4? Fault current. We just got that, right? 1.15. So what is this calculation? How much are we getting? 0.5 into 1.15. Those who have calculators. See, there is a J here also. Okay. And then overall it will be minus sign. So I'm just for the time being only worried about the magnitudes. So just magnitudes. So how much is this? 0.5 into 1.05. 0.5 into 1.05. Sorry, 1.15. And then subtract it from 1. I already know the answer, so I am just trying to wait for the correct answer. Is it 0.405? It should match to this one. That means the other one was wrong. 4 to 5. So what happened in the previous this thing? Did we make a wrong step earlier? Point 1, 0.25, 0.05. Anyway, I think it might be a calculation, this thing. So most of you are quite slow at calculation. So I think we made a mistake previously. So shall we repeat that once again? So if there is a fault here, 0.25, 0.1. So 0.35 into 1.15. Yeah, I think we are getting some different answer now. Anyway, let's try the other things. Let's try V2. What is V2? According to this formula, V2 will be 1 minus 24.6 into 1.15. So can someone do this calculation? This is also not matching. This should be 0.29. I don't know, somewhere we might have, it must be a calculation, this thing. 1.17 current. This is 1.17. So if this is increasing, if this is 1.17, then what happens? Is it good news for us? Yeah, here also it will change and all. So basically it was 1.15, 1.17. So it's not my mistake, you are calculating it. Anyway, but then see, out of the blue I just wrote this formula. So how this formula is coming? So let's think about that now. How this formula is coming? Okay. So it's quite simple. What I'll do is, maybe I'll use this place now. So look here. So we have Ohm's law. So how is Ohm's law coming? V equal to Z into I. So this is your Ohm's law. V equal to Z into I. Then we have just putting matrices. Okay. So the voltage vector is equal to impedance Z plus. We already seen this before. Now you consider that there is already a base case and then there is some variation or some kind of differentiation. Okay. So I can write it like this. Change in V is equal to change in V. Okay. So if there is any changes in the current, the changes in the current will be related to changes in the voltages because there is a constant coefficient defined by the network. So is that okay? It is like y equal to mx and then the delta y equal to m into delta x, something like that. It's linear. Now in this case, if there is a fault, so there is some fault current here. Okay. So I can write it like this: 0, 0, 0, and then I dash, lambda dash, 0, 0, 0, something like this, depending on the size of the resistor. Okay. This one here, so bus number K, there is a fault. If there is a fault at bus number K, the current injection at other buses is not changing. Just that only this delta, this one is changing. But I don't know what is this value. Now, as a result, what are the changes in my voltages? So these are all zeros at the beginning. And then, actually this is unknown. So I write delta V1, delta V2, and so on. And then delta Vk, and then so on. Okay. How much is the change in the voltage of bus K? Whatever is the Vk before, that Vk will become 0.
the change in the this term? It's nothing but minus Vk. It was plus Vk, then minus Vk, it becomes J, short circuit. So this one I know, the other side of it. Okay, so these are unknowns, these are unknowns. This one is known. So if I take only this is Z plus. If I take only this row, okay, if I take only this row, then what happens? This is minus Vk, change is minus Vk, and also there will be minus If because this is current injection, but then here I am withdrawing the current from the network. I am not injecting the current. So all of them are others are all zeros. So only which term will multiply with I? ZKK. So is equal to ZKK into minus I. Okay. So this is a simple this thing. So if I want to find out fault current, I can simply do this one. So V by Z. So Thevenin's voltage divided by Thevenin's impedance is equal to my fault current. So same thing. So what is IF? IF is nothing but VKF before the fault divided by ZK. So pre-fault voltage divided by the Thevenin's impedance. That is your fault current. And once your IF is known, now the IF is known. So you know this. Then I can find out what is delta V. What is delta V? Just look at this row. This row is getting multiplied by this part. Okay, but then all of them are zero. So only the Z1k. So Z1k will get multiplied by this I. So give me what is the value of delta V. So what is delta V1? What is delta V1? See nothing but Z1k into minus sign IM. So this one. What is final value of V1? So this is delta V. So what is V1? After this one, the previous value will minus this value. So somehow that is so in that sense, what was the previous value? Minus this one. I think somewhere we have to take care about the minus sign. So old value of V1 is we are already there. So I think that is also equal to 190. So V1 I can let's this is J. So if I'm interested in J here, then I use ZJ. Just J. I want to match this. So this is change in the voltage. So this is the final voltage. Will be old voltage. So maybe this is VJ. Minus VJ after the fault is nothing but pre-fault voltage. So let's put it VJ 0 and then minus this one and JK. That is how this thing is from this thing. In fact, you can do one more thing. You can directly calculate this vector. So what is this entire vector? Just multiply this with this. So you will get that this column is getting multiplied with this IM. So in one step I can find all this data. So you are supposed to get this number. Okay, at least the zeros will get because 1 minus 1 by 0.85 to 0.85, 0.85 can. It is this parts will get correct. Yes, question. This one? Because the change in the current injection, we are only assuming at this point, this was this is one. The current injection immediately after the fault. We are not So there is a mechanical input, PQ. Some mechanical power is input and then this is converting into electrical energy. But immediately after the fault, within the 2 millisecond, 2 cycles, like 20 milliseconds, 40 milliseconds, during the short duration, this mechanical power will not change. It will be same as before. So whatever new current is coming, that is coming out of only the stored in the rotation of that machine, whatever is stored, that is coming out of this machine. So that is why for the small duration we will not consider this other currents. That is the reason why that's kept. So that this is only for the small duration before the circuit breaker is open. So what I want to do next is just we'll just repeat this thing with one another problem. Then so let me get this one. Okay, the question is why do we assume that one angle 0 on process? So normal case you should not do that. You should solve the load flow problem first, and the results of the load flow problem you will get the voltage magnitude angle. That you should use for the rest of the So we are just doing here because we are only interested in just understanding the concept and yeah, that was also another reason that normally the voltages will be less, but then when I want to design the circuit breaker, I want more current to be there so that my design is more safer. So you can do it accurately, but then for the purpose of designing a circuit breaker's rating, you can directly take the one. That's another thing. Most of the things, steps like these assumptions are not made to simplify. Okay, let's just quickly look at another problem. It's something very similar. So I'm directly giving the Z plus into the small one. I'm just taking only the first two decimals. 0.1, 0.5. So I can just repeat this. How much should be fault current? So, see, just imagine that there's a bus loop. So, Thevenin's equivalent, you can just think. So, it is VTH by ZTH. So, that will be 1 divided by 0.23. I'm only interested in magnitude because distances are all negative. So, 0.23 is coming from here. So, how much is this? 4.3. So, so now you can see it is 4 per unit. And then, if I want to get the voltages, V1, V2, V3, V4. So I will take because the fault is in the second bus, I take this fault, second fault. So I think the current calculation is something like we have written one. So that is DJ is 1 minus Z JK into IF. Okay. What is IF? IF is just now what we have written, fault current. So that is 1 divided by Z KK. Okay. So if I take 1 common, then it will be something like this. So this is your VJ. Voltage of bus J will be. So here I just write the same thing. So 1 minus. So this one 2. So 0.19 divided by this one 0.2. Okay. So this will be 1 minus 0.23 divided by 0.2. So this will anyway cancel and your V2 will be changed. Because the 40 is at V2. This one will be 1 minus. What is this one? 1 5. 1 minus 10. So this is the direct step to the same thing to get it faster. I have you followed this one. What we have done. It just comes from the previous. So this is 1 minus 0.23. So how much is this quantity? I'll write down the answer. Save some time. So this will be 0.115. What's 5? So 34.9% of the voltage. So this is how you will. So if I want to, if I ask you to do the same thing without using networks, it will take a long time. You have to take the circuit, you have to solve it, and this was just a short problem just to repeat what I said. So let's look at one more quick problem, and that will be the last one. So I'll explain the situation like this. So there is a generator, and there is a this is a synchronous machine generating the power. So there is a circuit breaker. There is a bus bar. Then there is another circuit breaker, and then there is another. So this is a synchronous motor, not the generator. So let's regulate M1. So this is G1. And then there is another circuit breaker. And then there is a synchronous machine. This is a motor which is M2. So now the fault can occur anywhere. fault is occurring, then we point, we need to make a point which says point Q, and then let's say point P, and then point R. Let's call this circuit breaker A and circuit breaker B. Okay. So if the fault occurs at point P, okay, if the fault occurs at point P, now these all machines, even though they are motors, they will act as generators during that small period of time because they are synchronous machines. So what will be the direction of the fault current if there is a fault at point P? So let me just mark that. So there is a fault at point P. The fault current comes like this. From G1, it will pass through this, pass through this, and then pass through this, go to the fault. So this is one fault current. Another part of the fault current comes like this, goes like this, it goes like this to the fault. Another fault current comes from this machine, goes like this, and goes to the fault. So this is the total. Okay. Now, if you look at the circuit breaker B, it is looking three fault currents. There is another fault current from this to directly this. So that's also there. For the timing, we just see that B, because of its location, it is looking at three fault currents. One from here, and one from here. Whereas this machine A, the circuit breaker A, only looking at this fault. Whereas this circuit breaker only looking at this fault current. This circuit breaker only looking at this fault. Now, you have to coordinate the designing of these circuit breakers such a way that we should open. There is a fault current here, there is a fault current here, there is a fault current. All the three of them are looking at the fault current. But what happens is you open this circuit breaker. If you open this circuit breaker, the machine F1 will not receive any power. Right? It is a larger. The problem is not here. The problem is here. So ideally, what should happen? Only B should operate. Then the other three should remain closed. And if the B is operating, then the fault is separated. And then this suddenly the B is open, the fault current suddenly becomes zero. And then the normal current keeps up. And then there is no interruption. So this M1 and M2. M1 and M2 not interrupted. So you should design the. So what if you design it in such a way that the A itself opens? So if A itself opens, then all the three machines will open. So depending on the fault current, so if there is a heavy fault current, then that should operate first. So there should be some kind of coordination designing this. That's just a point. What if the fault is at Q? What happens if the fault is at Q? When the fault is at Q, so there will be one fault current like this, another fault current like this, another fault current like this. From machine 3, it will come like this, and then another fault current like this. So all four, there is a fault current. This circuit breaker, this circuit breaker, all four. So if there is a fault at Q, which one should open? Which circuit breaker should open? If there is a fault at Q. So all the four should open. But most importantly, A should open. Because what happens is, these are anyway machines. Okay. So if you look at the mechanical side, this is the electrical. Mechanical side, there is a, this is B mechanical going into the machine. Okay. So that mechanical energy can be used to send further power. Here I am taking the mechanical power outside because this is a motor. So I am taking the mechanical power outside. So even if I don't open this, so initially there is a fault current, but after that initial short period, further current will not come because this other side is here. So more importantly, A should operate first, and then other things, they even if they are seeing fault current for some time, but they will not. So this kind of thing. So, and what if there is a fault in R? If there is a fault in R, same thing. A should operate first. Any also notice that directions keep changing. Fault current. Sometimes the fault current going in that direction, sometimes fault current coming in this direction. So seemingly simple things are actually quite complicated when you go into the details. So there is this separate field called protection engineers. Okay. So protection engineers. So they are the more specialized version of electrical engineers. So a normal electrical engineer will be able to solve the problem before application of the faults. What will be the voltage, what will be the current, and all this. But then suddenly somebody says there is a fault, and then now you do it, and we need more involved studies. And still, I think we still have some 10 minutes time or 5 minutes time. So maybe then we will not go into detail of that. So one thing you can think about is we will not solve the problem. I'll just explain the approach how to solve the problem. See, is there a jet bus for the system? So we don't have jet bus because there is only just one single node. So we don't worry about making a jet bus. We can actually solve it right in the form circuit. So if I go for reactance for the fault calculations part, the reactance diagram will do something like this. So the machine is short circuited, and then there is one reactance, there is another reactance, another reactance, another reactance, and these three are also short circuited. And if there is a fault, this fault P, so the point P is located somewhere here. So then the question is how much is the fault current? Okay. You have to find the Thevenin's equivalent impedance. Let's say this value is given 0.2, 0.2, 0.2, 0.2. I'm not writing here. So what is the Thevenin's impedance at this point? So from here to this, from here to this, from here to fault, and then from here to this. So basically all these four are in parallel. Okay. So 0.2 parallel 4 times. That will become 1/4 of that. So 0.05. So your fault will be before fault the voltage it can be 1 divided by 0.05 because 0.2 by 4. So this will be how much? So this will be 0.2 divided by 4. So I think it is 20 per unit. Then 20 per unit. 4 by 0.2. So this much fault current will go. So if there is a fault at point P. So where it will flow, the 20 per unit will be here. So how much per unit in circuit breaker A? That will be in this 20 per unit. So you have to kind of solve this to find this current. I think no, actually our calculation there is a machine here, there is a machine here, there is a machine here. This current is like this, and then there is another machine here. So three are like this and one is like this. So if you look at the point B, 5 per unit is coming from left, and then 15 per unit is coming from like this. And then total fault is 20 per unit. So this kind of thing. I think you are getting the idea. So all this discussion is for the symmetrical faults. So sometime back in one lecture we saw unsymmetrical system, what are the components. Maybe a brief idea of that also I will try to. So next class we will